Let's review metabolic thermodynamics and interpreting metabolic pathway diagrams. These fundamental concepts will allow you to understand a lot more than you thought you did. By looking at a pathway and a big old network of pathways that looks really scary, if you know how to interpret the arrows and if you know the thermodynamics behind things, then you can really deduce your way through a lot of different situations. So let's dive in. At its heart, metabolic thermodynamics is just that good old natural thermodynamics that you learn in your general chemistry classes. For any generic equation, you can write an equilibrium ratio that is the ratio of the concentration of the products to the concentration of the reactants, but you need to take them to their stoichiometric coefficients and you have to multiply them. And so easier to explain with the picture than in words. And so something like this. And so we often abbreviate it just product over reactants, but that is going to actually be a simplified depiction of something that looks more like this. Now, if you take the concentrations at equilibrium, so you take these A and B and or you take some of C and D, it doesn't matter, you have some mixture of these combination of things, you stick them in a pot, you let them react, you give them long enough so that they reach that equilibrium where the rate of the forward reaction is equal to the rate of the reverse reaction, so the concentrations of each of these things is remaining constant. You take those concentrations and you write this equilibrium ratio. And so this KEQ, remember a capital K is telling us we've got an equilibrium constant. This is our equilibrium constant, our equilibrium ratio. KEQ is at equilibrium. The concentration is at equilibrium. I'm stressing this at equilibrium because you can take one of these ratios at any point in time. You can get this ratio of products to reactants that we call Q or the mass action ratio. So this Q is at any point of time. And KEQ is Q when you're at equilibrium. So Q tells you where you are currently in terms of the concentrations of products and reactants. KEQ tells you where the equilibrium lies. So what are the concentrations of products and reactants at equilibrium? And then things are going to react favorably. When I say favorably, think negative delta G, they're giving off energy, they're exergonic, in order to get from Q to KEQ. So remember, Q is where we are now. And so that's going to be our concentration of products to reactants right now. If Q is less than 1, that means that we have more reactants than we have products. If Q equals 1, we've got equal amounts of products and reactants. And if Q is greater than 1, there are more products than reactants. And remember, this is where we are right now, or under the given conditions. Now, KEQ, this is going to tell us where the equilibrium lies. Similarly to with Q, if KEQ is less than 1, we've got more of our reactants at equilibrium. So now instead of looking at where we are right now, we look at where we are at equilibrium. If KEQ is less than 1, we've got over here, we've got in that zone where we've got more reactants than products. If KEQ equals 1, we've got equal amounts. And if KEQ is greater than 1, then we've got more products than reactants at equilibrium. So KEQ is at equilibrium. Q is where you are right now. Now, remember that things are going to react favorably in order to get from Q to KEQ. So we need to compare our Q to our KEQ in order to know which way is going to be favorable. And so if our Q is less than our KEQ, so if we have a Q that is somewhere over here, but then we've got a KEQ that's somewhere over here, this reaction, in order to reach equilibrium, it's got to make more products. If you're going in that forward direction as written, making more products, then we say it has a negative delta G, it's exergonic, and we're going to be reacting in a way to make more products that is in the forward direction. Q equals KEQ. Well, that means that we have amounts of our products and reactants as we would have at equilibrium. It's not saying that we have equal amounts of products and reactants. It could be very unequal, but we're at the equilibrium values. Because now we're comparing Q and KEQ, so it could be that we have it over here, and it could be that we overhead over here, and we could have it over here. But the key thing is that what we have now is equal to what we would have at equilibrium. But if our Q is greater than our KEQ, this means that we've got more products now than we would have at equilibrium. And so we need to actually go backwards. We need to make more reactants, break down those products to make more reactants. in order to reach those concentrations that we would have at equilibrium. So our reverse reaction would be favorable. Our forward direction would be unfavorable. We'd have a positive delta G. Now, what about standard conditions? And so this little knot symbol indicates standard conditions. There are various things that go into standard conditions, but the key thing that you need to know to understand all of this is that at standard conditions, all the reactants and products are at 1 molar concentrations. Note that there's also this biochemistry standard conditions, which is saying, okay, we'll be a little more reasonable and we'll say that you can have the pH is equal to 7, so the proton concentration is 10 to the minus 7 molar. Water is 55.5 molar, magnesium is 1 millimolar. And we typically indicate that with this prime symbol. But we often use these terms interchangeably, and so I'm not going to try to trick you with that or anything. If you see that delta G naught, or you see delta G naught prime, that's telling you your standard conditions. Bottom line, for most things, you're going to have 1 molar concentrations of everything. And if all your concentrations of your products and reactants are 1, well, then that's going to mean that your Q is 1. And Q is only going to be 1 if you are under standard conditions. But typically, you're not going to be at standard conditions, but it's useful to know the standard condition free energy changes because then we can use those to calculate the actual free energy change, the actual delta G, if we know the concentrations of products and reactants, that is our Q, and we know the standard free energy change, which we can look up in a table. So our standard conditions are now our Q, and we compare that to our KEQ. We see that if our KEQ is less than 1, we're going to have to go in the reverse direction in order to reach that equilibrium. Our delta G naught is going to be positive. If our KEQ is equal to 1, then our delta G is going to be 0. We're basically at the same place. And if KEQ is greater than 1, we're saying that we start here and we need to get here, so we need to make more products. That's going to be thermodynamically favorable, negative delta G naught. Okay, but remember, standard state is not equal to equilibrium unless you have that KEQ equals 1. And then you're saying you're at the equilibrium. Equilibrium equals your standard state. At your standard state, you have equal concentrations. And so at equilibrium, if you had equal concentrations of everything, then you would have that. The standard state is equal to equilibrium. KEQ is going to be 1, and delta G naught is going to be 0. But standard state does not equal normal, it does not equal typical, and typically we're away from standard state. And so if you want to visualize this, you can use pieces of candy and think about how many pieces of candy you'd have to move. If you start from that standard state where you have equal amounts of reactants and products, how many pieces of candy would you have to move to one side or another in order to reach a KEQ of different values? What you'll find is that the further you are from equilibrium, the more energy is released when you react to reach equilibrium. So you have to move more pieces of candy. But the harder it is to go back the other way, because the delta G for the reverse reaction is equal in magnitude but opposite in sign. And again, you can work your way through thinking about things with, if you're a visual learner, you can do things with pieces of candy and think about going, which direction do you need to go? And if you need to move the same amount of candy pieces, that is going to be equal in magnitude of your delta G. But depending on which way you're moving them, are you moving them to the right? Are you moving them to the left? That's going to be the sign of your delta G. But you can see that kind of the further you are from that equilibrium, the more pieces of candy you're going to have to move, the more energy you would release in order to reach equilibrium, or the more energy it would take to get away from that equilibrium. So we have this direct relationship between the KEQ and the delta G naught. The delta G naught, remember, that is the energy from going from our standard conditions to where we would be at equilibrium. That's the energy that's given off. The further that the equilibrium is from the standard conditions, the more energy will be given off in order to get to equilibrium. So the further you are from equilibrium, the bigger this distance that you go in order to reach equilibrium, the more energy that's given off. So it also means that it's going to take that much energy to go in the other direction. So let's think if we have a really favorable reaction. We've got a KEQ greater than 1, meaning that we have more products than reactants at equilibrium. Our delta G naught is going to be negative because we would release energy to go from our standard state to equilibrium. So if we had equal concentrations of things, we would be going to the right, making more products. What if we want this reaction to go to the left? What if we want it to make more reactants, break down the products and make reactants? In order to do that, we would have to make it so that we were even more extreme than this already extreme ratio. We'd have to make it so that we have even more products than reactants than we would have at our equilibrium. And so these would have to be really, really unrealistic concentrations of things in order to get things to go in the other direction. Sometimes it can help to think about extremes. And so if you think about a condition where you don't have any reactants, then all you could do would be to go backwards. But you only need a little bit of reactants, and then this is going to make it so that the forward direction is going to be favorable again. So when you have these reactions with a really large delta G naught, just changing the concentrations a little isn't going to be that impactful, at least changing them in the physiological range. And so rather than trying to control the directionality by controlling these concentrations, we're actually going to control the enzymes to make it so that you can kind of react or don't react, but not go this way or go that way, because enzymes cannot control that. Enzymes can only lower the activation barrier. They cannot change the overall delta G. They cannot change the delta G naught, but you can change the directionality of things that are more in this zone where the concentrations can really do few things under physiological conditions. Then you can have metabolically reversible reactions, which we'll talk more about in a minute. So the key thing is that it's a combination of the current conditions and the inherent favorability, this delta G naught or the KEQ. Remember those, you can go back and forth between delta G naught and KEQ values. And the current conditions, so our Q values, those are going to be combined in order to give us our actual free energy change. And the more extreme the inherent favorability in one direction or another, the harder it is to change the directionality by changing the concentration of products and reactants. So the further you are from equilibrium, the more energy is released when you get to equilibrium. But that also means that's going to take more energy in order to make the reaction go in the opposite direction. So you're going to have equal and opposite magnitude of your delta G. And you're going to think about things typically in the direction that is written unless otherwise indicated. So the things on the right are going to be considered your products, and the things on the left would be considered your reactants, unless they say in the reverse direction or something like that. Now, things are going to react in order to reach that equilibrium. But if things are at equilibrium, there's no drive to do anything, no metabolism, no life. So life is driven by this desire for equilibrium. But once reached, life has ceased to exist. So we need to keep equilibrium out of balance if we want to have life. How are we going to do this? Instead of having equilibrium, we're going to have this steady state. Steady state keeps constant levels of metabolic intermediates despite being away from equilibrium. And so in equilibrium, you have a closed system. So if you think about stagnant water in a pipe, whereas steady state, you have water flowing through a pipe. It can happen by forming and consuming or otherwise removing the intermediates at equal rates. And so you can be adding water in the pipe at the same rate as you remove it. And as long as you're doing this at the same speed, you can kind of have this be have some sort of concentration that's kept steady. But it's not going to be the equilibrium concentration necessarily. If you think about your pipe, and instead of thinking about it vertically where we have to think about gravity helping out that one down direction, let's think about our pipe being parallel. So this is kind of if we had a delta G that is going to be 0. If we add water over here, then it's going to push the water to the right. And if we add water over here, we can get it to flow to the left. So that would be like a metabolically reversible reaction. Just by changing the concentrations of our products and reactants, we can control the directionality of the reaction. We call this thermodynamic regulation. Now, this would not be enough if we had a condition where we had something that was really skewed. These skewed conditions, we have metabolically irreversible reactions. These typically have large delta G values, and the directionality cannot be controlled just by controlling concentrations. We'd have to add a ton of water over here to get the pipe to flow through this way, We have to add a ton of water over here in order to get the water to flow through the pipe to the right. So instead of changing the concentration of the water, what we can do is we can kind of just tap the spigot or have it open. And so the metabolic equivalent of that would be regulating the enzymes that catalyze the reactions. So remember, I hate that term spontaneous because it seems to imply that things happen instantaneously. But remember, we've got the activation energy, the activation barrier, and the enzyme can make that activation barrier smaller. So the enzyme can kind of uncap the pipe, but that's going to make it so that water can flow in both directions. It's going to help out in both directions equally, but you're still going to have to push a ton of water in order to get it to go the other direction. But if you have an enzyme that's going to make it so that you can go through the pipe, then it's going to go through in the direction that is thermodynamically favorable. But then you're still going to be hard to go backwards. Okay, so that would be a metabolically irreversible reaction. We're controlling the enzymes. We call this kinetic regulation. Another analogy that might help is we think about a series of swinging doors, and I have these series of swinging doors. Now, instead of a single reaction, we're thinking more about a pathway, because in metabolism, we're often talking about these pathways where we have these interconnected reactions happening. And so we think about each of the products of one reaction or the reactants of another, and the products of that reaction or the reactants of the next. So we think about all of those reactants and products as kind of intermediates. If we have this pathway, if we've got metabolically reversible reactions, think about them as swinging doors. You can easily go through the doors from one way to another, but then you meet an irreversible reaction. You've got a door that only has a handle on one side. And so if you go through it, you're kind of stuck on that other side. Technically, yes, you could go back through the other way if you put enough force and you push through that door, but you'd have to put in a lot of force in order to do that. And that's not going to happen. So you're going to have to go and find another door, take a detour to go the other way. If you run into these one-way doors, these no turning backs places, these metabolically irreversible reactions. So we're going to want to regulate the enzymes that control whether their door is locked or not. But then you can go and you can have some more swinging doors. So on either side of when you have these reversible reactions, you can go back and forth, just like call someone from this side or from this side, and they'll go back and forth. But then if they wanted to go back all this way, they'd have to go around. So enzymes can kind of grease the hinges on the swinging doors, making it easier to go back and forth, but they can't control which way you want to go. And so that is going to be related to the thermodynamics. That's going to be related to your Q versus your KEQ. And your KEQ is related to your delta G naught, your inherent favorability. And you can control the Q, but you can't control that KEQ. You can't control the delta G naught. The enzyme can only change the activation barrier. It can't change the overall delta G. It can't change the overall delta G naught. And so then if we have this metabolically irreversible reaction, now the enzyme can unlock the one-way door and it can make it slightly lighter, but the door is still too heavy to push back through in the other direction. So if those analogies work for you, great. If not, think about an analogy that does work for you. Let's start thinking about now how we kind of can talk about reaction pathways. So as I mentioned, all of the different molecules in these pathways can be considered intermediates. The products of one reaction, then reactions of the next, and all these various things. So we just refer to them all as metabolic intermediates. These are different than enzymatic intermediates. When we think about metabolic intermediates, here we're really thinking about all of these different molecules in the pathway. And I'm talking about pathways, but you can see that they're really interconnected. And so an intermediate can be an intermediate of multiple pathways. So there's a lot of regulation that goes into directing where things go. And some of it is dependent on the concentrations, and that's going to be influencing our thermodynamic regulation of our reversible reactions. And then some of it is acting at the level of the enzymes, controlling those irreversible reactions. So how do we know if a reaction is reversible or irreversible if we don't know the delta G naught, if we don't know the KEQ, all these various things? We can know just by looking at these diagrams. So let's talk about the hidden language of metabolic pathway diagrams. In terms of our biochemical reaction notation, double arrows, or if you have one arrow with arrowheads on both sides, that's going to be indicating a reaction is metabolically reversible. If you only have a single arrow, this may or may not indicate a reaction is metabolically irreversible, meaning that delta G is too large to overcome under typical physiological conditions. Warning, sometimes you have single arrows, and that's not because it's irreversible, it's just that it's easier, or that you want people to think about it in the forward direction, or that you don't know if it's reversible or not, things like that. So sometimes you don't know that, but if you're in the context where you have a lot of double-headed arrows and then you have a single-headed arrow, that's a good sign that it is going to be irreversible. And we'll talk about some other signs. I'm not going to try to trick you. And so I will indicate if I do have a single arrow, I will say like this is not to indicate reversibility or anything like that. But if I have a diagram with both of these, the single arrow is indicating that it's metabolically irreversible. Another sign is that the names of enzymes are typically written above or below the lines. And so if you have two lines and each of them has a different enzyme name on it, then it would be indicating that each of these arrows was a separate irreversible reaction. But if you have a single enzyme name with the double-headed arrows, then it's indicating that it's going to be metabolically reversible. And we'll look back at an example in a second. Another thing you want to look for is certain cofactors and other participants. And so if often you're going to have something like ATP or have something like NADH, the products and reactants, those that are kind of contributing to this reaction, helping the enzyme out. Again, we'll look at an example. These are going to be drawn with these curved lines that are going to be above or like kind of attached to the main arrow. So let's look at an example because that makes things a little easier. And so this is the one from our SOCs. And we have these two reactions that are written here. And we see we've got a lot of arrows going on, and we've got some molecules. These bold things, these are just the names of these intermediates. If we see this ending A's, that's indicating we've got enzymes. And we can see that we've got enzyme names written next to the arrows. Looking here, we've got some sort of other molecules that are involved. We've got some cofactors, some ATP, we've got some ammonia, things like this. But we can actually figure out a lot just by thinking through things. So we said that the name A's is indicating an enzyme, as well as it being next to an arrow. A lot of times you'll see abbreviations for things, but in this case, we get to see that it is an A's, it is an enzyme, and we have it next to an arrow or below or above the arrow. And so these are going to be our enzymes. Now we need to think about which of these reactions are going to be metabolically irreversible versus which are going to be reversible. So irreversible, remember there, that's saying that we're going to have this single arrow, or we're going to have a single arrow associated with an enzyme. And so in this case, we have a double-headed arrow. This one's indicating that this is reversible, easily reversible. Here, this one's the simplest. We have a single-headed arrow, we have a single arrow, and a single enzyme. So this is going to be metabolically irreversible. What about these? These are also going to be metabolically irreversible. There's a couple of hints about this. The first is that we kind of have two enzymes. So there's one enzyme associated with each of these lines. And then each of these lines, it kind of has a different reaction is actually going on. So you can see that we're using ATP in this forward direction, but we're not using it in the reverse direction. So these are going to be catalyzing these irreversible reactions. Now let's think about this. We actually have this shared component, this glutamine, that is a shared component of this reaction and this reaction. So we can make glutamine based on glutamine synthetase, or we can make glutamine based on glutamine transaminase. But what about glutaminase? Could we make this reaction go this direction? No, it's indicating that it's metabolically irreversible. And so we couldn't just go and make it go in this direction without totally messing up everything else that was going on in the cells. So we could only use glutamine synthetase and we could only use glutamine transaminase under physiological conditions in order to make glutamine. I mean, at least out of these options. We also saw that we were kind of using ATP to make it go in this forward direction. This is an example of what we call reaction coupling. And so reaction coupling is when we use the energy from favorable reactions in order to drive unfavorable reactions. And we can do this because free energy changes are additive. And so as we'll discuss in a minute, and as we discussed, the hydrolysis of ATP is going to be energetically favorable. It has a large negative delta G, it gives off a lot of energy, and that energy is used to power unfavorable reactions And so the energy from the ATP hydrolysis can be used in order to make our glutamine. So this must be energetically unfavorable to stick on this amine group. And so the ATP is providing the energy in order to do so. So how does ATP give us energy? It comes from a variety of different factors. The key thing is that the energy does not come from breaking a bond. Breaking a bond is always endergonic. It's always going to require energy. It's always going to take energy in order to break off one of those phosphate groups. But it's the hydrolysis reaction overall that's going to be energetically favorable. And so the energy comes from the hydrolysis of ATP, not the physical breaking of the bond. We need to think about the actual reaction that's going on, the interactions of all of the molecules in the initial conditions and the final conditions. What happens is that if you think about ATP, you've got these three phosphate groups. They're negatively charged. They're tightly clamped. They want to get away from one another. And so if you break that bond, the breaking of the bond, the part where you're actually breaking the bond is going to take energy, but then you get energy released. You have that charge repulsion that's freed. You've got this phosphate group that's going to be hanging out with water and it's all happy. You've got good resonance. So all that is kind of making this inherently favorable. And then our cells actually keep the concentrations of ATP way higher than the concentrations of ADP in order to make them even more thermodynamically favorable. And so we can't change the directionality of the ATP hydrolysis reaction. We can't just stick the phosphate group back on the ADP to make ATP unless we put in energy, which we can do. We can do that. We could use the energy from redox reactions in order to do that. But we can't just change concentrations in order to do that. But we can control the amount of energy that we'll give off. And so if we think about our ATP hydrolysis, the delta G naught for that reaction is minus 7.3 kilocalories per mole. So under standard conditions, we would have way, way, way more ADP than ATP. But under actual conditions, we have ATP concentrations that are way higher than ADP concentrations. And this is going to make it so that our Q is way, way, way smaller than our KEQ. We're going to need to reach equilibrium, we need to go in the forward direction a lot. And that means that we're going to give off a lot of energy to do so. We're very far from equilibrium. And so we get more energy than we would get if we were under the standard conditions. So we get a lot of energy from the ATP hydrolysis. We get a lot of energy too from the hydrolysis of other phosphorylated compounds. And we can use that energy, we can couple that energy to unfavorable processes in order to drive those unfavorable processes. And this is often happening in the form of group transfers. So we are transferring those phosphoryl groups. And so remember that often we're going to be transferring a phosphoryl group. And so we're going to be transferring kind of this phosphorus with 3 oxygens rather than a phosphate group, the phosphorus with 4 oxygens. But then we're going to have that transfer that is going to allow us to kind of do things a little stepwise, but we still, because that delta G is going to be a state function, we get the same amount of energy. We can also use ATP and ADP and AMP as a way to think about how much energy our cells have and how much energy our cells need. And we'll get much more into this in future lessons about how ATP is going to kind of slow down catabolism, ramp up anabolism. So stop breaking things down and start making things. And in the reverse, if you've got a lot of AMP or ADP, but not a lot of ATP, you're going to want to make more ATP. So you're going to want to break things down to use the energy from the favorable redox reactions in order to make ATP. So just so how we said, like the farther you are from equilibrium, the more energy that you'll release to get to equilibrium. The bigger the difference in the reduction potential between an electron donor and an electron acceptor, the more energy that you'll get if you pass the electrons from one of them to the next. And you can use the energy from favorable redox reactions in order to power the synthesis of ATP through oxidative phosphorylation, the subject of other videos. You can also make ATP by transferring phosphate groups from other compounds whose energy from the hydrolysis would be even more favorable. You can use their energy from those reactions in order to actually phosphorylate ADP to get ATP from other organic molecules. And we call this substrate level phosphorylation, as opposed to oxidative phosphorylation, where we're transferring it from a free-floating inorganic phosphate group onto ADP and using the power of oxidation reactions, which we call oxidative phosphorylation. And typically when we talk about oxidative phosphorylation, it's happening through this kind of mitochondrial oxidative phosphorylation, driven by the electron transport chain, where you pass electrons through these different carriers and you pass them through these complexes, and then you pump out protons, you make a gradient of protons that's used to produce synthesis of ATP. There are other kinds of oxidative phosphorylation, but if we just use this term, that's why I kind of just talking about oxphos when I'm talking about it in this context. But don't worry about that for now. Just know if we think about oxidative phosphorylation, you're thinking about in the mitochondrial powered by the electron transfer chain. Okay, so let's get a little more into metabolism and look at some more examples and think about regulation a bit and pathway diagrams. So I've been kind of using some of these terms, and so let's go back and review some of these terms. We've got anabolism, where you're making molecules, and catabolism, where you're breaking down molecules. And we've got these interconnected pathways, where we've got some reactions that are going to be easy to go back and forth, these metabolically reversible reactions. And then we've got some reactions where we can see that we have single arrows, where we have single arrows with different enzyme names. We've got different reactions happening in the forward and reverse direction. So some reactions are going to be easily reversed and some are not so easily reversed. And so if we want to control this whole network, we've got to control the concentrations of things in order to control both the directionality of the reversible reactions and the energy given off by the irreversible reactions. And we need to control the enzymes of those irreversible reactions so that we can make it so that we don't go down a doorway we don't want to go down. Overall, pathways need to have a negative delta G, but we've got to be able to do anabolism. We've got to be able to build things at the same time that we need to be able to do catabolism, break down things. Not at the exact same time, but we need to have both the ability to do both of those things, depending on the current conditions. And some of those directionality is controlled by those irreversible reactions that we need to control the level of the enzymes. And some of the directionality can be controlled just based on the concentrations that we have. So a negative delta G in one direction, however, is going to be an equally positive delta G in the other direction. And so anabolic, that is building molecule, and catabolic, breaking down molecule pathways, cannot simply be inverses of one another. They can share a lot of the same enzymes and a lot of the same intermediates, but they're also going to have different irreversible steps. A great example of this is glycolysis, the breakdown of glucose, and gluconeogenesis, the making of glucose from non-sugar sources. Rather than reversing those irreversible reactions, our cells are going to take alternate routes around them. Remember, we've got that door with a handle only on a single side. We've got to find a detour door to go around. We saw an example of this when we were looking at a glutamine synthase and a glutaminase. These were going to be irreversible reactions in both directions, catalyzed by different enzymes. And not only are they catalyzed by different enzymes, but we can see that they're actually doing different reactions. Our ATP, ADP is only associated with one of the arrows and not the other. Another example, we have our glycolysis and gluconeogenesis we were looking at. They use 7 of the same enzymes, but they're not simply reverse of one another. We can see that we've got different reactions happening here, we've got different reactions happening here, and we've got different reactions happening here. For example, in this case, we are using hexokinase to transfer a phosphate group from ATP onto glucose to give us glucose 6-phosphate. But to go the reverse direction, rather than trying to stick that phosphate group back from glucose 6-phosphate onto ADP, which now we don't have enough energy to do, we're just going to hydrolyze that phosphate group off using water. And we're going to use a different enzyme in order to do this. We'll talk a lot more about regulation in future lessons. And so for now, I just want you to know kind of thermodynamic regulation, where we're regulating things based on changing concentrations of products and reactants, versus kinetic regulation, where we're regulating enzymes. And we can be doing things like activating enzymes or inhibiting enzymes. This can involve things like post-translational modification, things like phosphorylation, maybe by signaling pathways, as well as then allosteric regulation, where we have small molecules that are binding and influencing the activity of the enzyme. So you've got a little molecule bind to you, and that molecule makes you have a conformational change shape a little, and that's going to influence your activity. You can also have transcriptional regulation where you either make more of the enzyme or you stop making the enzyme. You can also have things like compartmentalization. So maybe you only have that enzyme in the mitochondria, various things like this. And so we can see the activation and inhibition in the form of arrows in our diagrams. So often for activation, you'll see something in green. In inhibition, you might see something in red. Not always. Activation, you're often going to have these green arrows, and inhibition, you're going to have kind of this sort of sign. And note that I'm showing you all these various things, not to confuse you, but because there's so many different ways that things are depicted in diagrams, and you just kind of need to be able to figure out based on what is being shown. And so I use a lot of real life examples, and I just draw figures from various sources. And so that's why they're not always consistent, is because in the real world, things are not always consistent. And I want to prepare you for that real world by using these real world examples. So look for any of these sort of symbols for activation and any of these sort of symbols for inhibition. At this point, I don't need you to recognize feed-forward stimulation or feedback inhibition, identify them as such. We will do a lot on that though. And so that's going to be assessed in future assessments. And so I'm just going to do a quick review here of it. With activation, you'll see things like feed-forward stimulation, where an upstream intermediate is making it so that a downstream enzyme is going to be activated and ready to catalyze a reaction that's further down in the pathway. Feedback inhibition is when you have something downstream in the pathway that's inhibiting something upstream. And so you can think in terms of supply and demand. The feed-forward stimulation is saying we've got a lot of demand, and so those workers at the end of the assembly line get ready. And then the feedback inhibition is saying your supply is way, way, way outpaced your demand. Stop making me make more. And so if you want to think about an assembly line, you've got workers at a variety of different steps. And if you don't have any parts to put together, then these workers at the end of the steps are sleeping. Maybe they're not phosphorylated. But then you get your parts in, and so you're not ready to use the parts yet over here, but you're going to wake up those workers that were sleeping. This would be feed-forward stimulation. You've got these parts that are going to be waking up the workers downstream. But then you start making things, and maybe you made enough, and now you've made too much. And now you're going to say, these workers are going to be like, hey, we've made so many. We've got way more than you need. Stop making us do this and let us sleep. And so that would be feedback inhibition. So you've got these products of its downstream reaction inhibiting an enzyme upstream. In a more real life example, if we look back to our glycolysis and our gluconeogenesis, remember this is one of those steps that was going to be metabolically irreversible. So we're going to want to really control it. We can see that this hexokinase enzyme is going to be inhibited by G6P. And so G6P is going to be this glucose 6-phosphate. This glucose 6-phosphate is a product of this reaction that's going to be inhibiting the enzyme that made it. And so sometimes the feedback inhibition is for something that is an enzyme further, like several steps upstream, but it can also just be the direct product of a reaction. And similarly with activation. But in this case, we've got an example of activation of pyruvate kinase by this F16BP. F16BP is this fructose 1,6-bisphosphate, which was an intermediate that was upstream in the pathway. And so pyruvate kinase is activated by an upstream intermediate, fructose 1,6-bisphosphate. Those are the key concepts, and now let's go and review some of the SOCs. Based only on this figure, would adding glutamate increase glutamine production? So if we add glutamate, would we make more glutamine? Let's look at how we get from glutamate to glutamine. We can see that we can make it with this glutamine synthetase. If we add more of our reactant, go to Le Chatelier, says we're going to make more product. In this case, we aren't told anything about enzyme regulation or anything, so just imagine that these enzymes are all active. So if we add more of the reactant, we're going to make more of the product. So yes, this would at least temporarily increase glutamine production. And I say at least temporarily because when you increase the glutamine production, then you're going to also increase the activity of glutaminase if these aren't regulated, which is why you really need to regulate things. Based on this figure, would adding alpha-ketoglutamate, man, I don't know how to even pronounce that, would adding this increase glutamine production? Yes, alpha-ketoglutamate is going to be a product of glutamine transmaminase in the forward direction, but it's actually going to be a reactant in the reverse direction. And so if we add more of this is metabolically reversible. It's going to push the reaction in this reverse direction. We're going to make more of our glutamine. What about if we were to add alpha ketoglutamate? So if we were to add this, would that increase glutamine production? No, because this is going to be metabolically irreversible. We can't just make it go the other direction by adding more of the product. Speaking of changing directions based on the concentrations, which of these reactions do we think would be able to do that? Control them thermodynamically. The only one is going to be the metabolically reversible one, and so that would be our glutamine transaminase reaction. What about kinetically? We still can control the other directions, but just not the directionality. But we can control which direction we go based on controlling which of these enzymes we activate or which of these enzymes we inactivate. And so these metabolically irreversible reactions, we can't control the directionality just by controlling the concentrations of products and reactants, but we can control the enzymes. We can do kinetic control to basically say, okay, you can go, or okay, stop going, and say if we turn off this, then we can turn on this, then we can make it go this direction. So things like that. Basically, kinetic regulation you do for metabolically irreversible reactions. You know they're irreversible because they've got those single arrows. Metabolically reversible reactions, you can just control the concentrations of products and reactants. A couple more examples. Which of these are an example of a reaction that likely has a large negative delta G? Remember that metabolically irreversible reactions are going to be associated with those negative large delta Gs. And so if we see these reactions with these single arrows, then in this direction, they're going to have a large negative delta G. That's going to mean that they're also metabolically irreversible, kinetically controlled, so we control those enzymes. What about ones with a small delta G? So this one, say in this one, we have these double-headed arrows indicating that we can go back and forth easily, that we have a small delta G, they're metabolically reversible, and we can control them thermodynamically. And note that if I have an example where I just say like an example of a reaction or something like this, you would only need to select one of these. Like as long as you had one arrow, you'd be good. I just wanted to put arrows so you could see which options you could have chosen. Okay, and now just a kind of fun question to end things off. Critical thinking. This is a pathway that is used to make these ketone bodies. And so basically these ketone bodies are a way that your liver can send fuel from fatty acids to your brains because your brains can't just take in the fat and use it that way, but they can take in these soluble carriers of the energy from that fat. And those are called ketone bodies. These ketone bodies include acetoacetate and beta hydroxybutyrate. Acetoacetate is actually really helpful, and you can actually use it in our bodies, and we can link it back up to make more fat. We can break it down and put it through the citric acid cycle, various things. So acetoacetate is really directly helpful. Beta hydroxybutyrate is not so directly helpful. But which of these do you think that your liver is going to be sending out to your brain? We can see that acetoacetate kind of splits off, and it has these two different reactions. This one is going to be an irreversible reaction that's going to give us acetone. This one is going to be a reversible reaction. So to make beta hydroxybutyrate, even though this might not be that useful right away, we can actually convert it back into acetoacetate. So if we send this, we can go back. If we send this acetone, we can't go back. And if we send acetoacetate and it goes through this spontaneous reaction that gives us acetone, we can't go back. And so your cells are actually going to send this beta hydroxybutyrate, and that's going to make it so that you don't have to worry about having acetone released and that you can't go back from, and then you have nail polish remover basically in your bloodstream. Also, by sending the beta hydroxybutyrate, you can see that you're sending it in this reduced form. And so you're adding electrons, and then when it gets to your brain has even more energy. When it converts it back to acetoacetate, it gets NADH, and it can use that NADH in the electron transport chain to make ATP. Booyah. So yeah, so I want to ask you a question that's hard. I just thought you might find it interesting. So hope that helped, and happy studying. And I know that there's a lot to wrap your head around, but hopefully this helped.